Starting here, we have Jane Charlton with a tutorial on multi-phase cloudy modeling. So take it away, Jane.
So this presentation is something that Samir, my graduate student, and I put together. So it's very much a collaborative effort. And it is very much a tutorial. It is not a presentation of current thinking or profound technical models. It's really painting a picture of how absorption profiles are shaped. And I believe that that is very important to sort of the next step in our ability to pull physical parameters out of these profiles. So here I just show a bunch of different chemical transitions, the Lyman series lines and metal lines spanning a range of ionization states, and the results from Samir's Bayesian cloud by cloud modeling and the contributions of different phases of gas to the different clouds. And so we're just going to briefly come back to this later. But the idea here is to explain how these profiles are shaped and how the different physical conditions of the gas change the appearance of the profiles. And so I'm just going to present a series of simple simulation models. But first, what do I mean by the physical properties? We're going to consider that there are clouds of gas that are shaping the profiles, and each cloud in each phase has a different number density. Metallicity, I'll always define that as 0 for the solar value for log Z. The temperature, which is determined in cloudy if in photoionization equilibrium, but we can have a higher temperature cloud where collisional processes are dominating. The line is shaped by the turbulent B parameter as well as the temperature. And then, of course, the abundance pattern, which is beyond the scope of what I'm doing here today. And then finally, thickness, which can be calculated from the total hydrogen column density divided by the number density. And I say thickness here rather than size because I think it's very important that many of these are nothing close to spherical structures. The main insights, and so if you already know these things, you can go out to the breakout room now. But I'm hoping to illustrate it in a way that might bring up new ideas. The idea is that the shape of these Lyman series lines very sensitive to the phase structure and their different contributions to these lines from the different phases, which means that there's hope of determining metallicities separately for different phases, even for superimposed clouds. The second point that I want to make at the end will be that if we are tracing absorbers by a particular ion, like magnesium-2 absorbers, carbon-4 absorbers, these are not produced by the same types of structures at different redshifts because of the evolving EBR. And so we really need to hold this into account when making interpretations of things like changing covering factors. Okay, this is the first series of models that I wanted to show, and these are just idealized simulations. In this case, I am showing a specific absorption cloud with a column density of 12.5 in magnesium-2. You see that there. The B parameter of the magnesium-2 is 3 kilometers per second. And I'm showing what happens to the other profiles for clouds of different densities listed here, from low to high density, which corresponds to high to low ionization parameter. And you see that carbon-4 is only here for the lowest density corresponding to the cloud, but yet the iron-2 is strongest for the higher densities. And so this sort of shows how the different transitions are used to figure out the density of the structure. Let me describe a little bit in more detail how we do this exactly. What we're doing is the very simple procedure of using an extragalactic background, in this case, Kearsley-Anand 18 for the purpose of this talk. Different background radiation shapes and amplitudes lead to slightly different results, but this is just a broad brush view of things. And that radiation field, we're going to start at redshift 1 here, is incident on a constant density slab, which has an assumed metallicity, a solar abundance pattern assumed. When it is incident on this, it of course affects the ionization state of all of the different transitions. In these experiments, we're always going to be specifying an optimized transition, which is going to be a metal line transition. And so the column density of magnesium 2 and the B parameter of magnesium are going to be specified. It's best to use a very high resolution data set to get the optimized transition, because that guides how many components there are. Then run a cloudy model, and cloudy will provide a temperature and column densities for all of the other species. And then that temperature, and this is an important point, okay, that temperature can be used to figure out from the magnesium profile what the turbulent B parameter is for that cloud. Once that is known, that turbulent B parameter can be used along with the mass of any chemical element, in this case hydrogen, to figure out what the B parameter is of hydrogen. Knowing that can break some degeneracies in inferring metallicity with cases where there are saturated lines. So using the metal lines to guide the B parameter of hydrogen and what that would be. So this is showing actually something very similar to the first series that I showed, with the only difference being the B parameter. This is a little bit broader magnesium 2 line, and it's not making a huge difference to the situation. In this case, though, the B turbulent is dominating over the thermal B for the magnesium, and the hydrogen lines, if we made a comparison, would just be a tiny bit broader. The thicknesses of these 4 clouds range from 50 parsecs down to 0.1 parsecs for the higher density. These are very, very small. Here is a plot that I think brings home the idea that we really can constrain metallicity. At least we can always place a lower limit on what the metallicity has to be. Because here we are holding the density fixed and varying the metallicity from -2, where you see tons of hydrogen necessary to produce the optimized Mg2 profile, increasing to -1, 0, and 1. And so what we observe the hydrogen lines to look like is definitely going to be very important in determining the metallicity. The thickness is very dependent on the metallicity, with even for the largest, in this case, it's 400 parsecs, ranging down to 0.1 again. So the thoughts about the low ionization phase from just looking at these examples, that the degeneracy between the Doppler parameter and the metallicity can be broken using the metal lines to figure out more about how broad these lines really are. And this is very important in cases where we might just have access to Lyman alpha and Lyman beta in the spectrum. can still do something even with Lyman alpha and Lyman beta, and there are ways of testing that, of course. The low ionization phase tends to contribute to the higher order Lyman series lines, and it also contributes, there's a little square bottom of the Lyman alpha that's important for these narrow lines, and that's why it does this, because these are very small B parameters typically observed at redshift 1. Values between, say, 2 and 8 kilometers per second are common. You don't get O6 from photoionized phases that produce low ionization absorption, though of course there are variants on photoionization equilibrium models that can, perhaps. And then some cloud thicknesses are quite small, meaning parsec scale, meaning that in most simulations, the cell sizes are bigger than these objects, which means that the low ionization absorption in simulations is often probing a different kind of structure than the real structures. So for low ionization absorption, there are going to be differences, which are going to be subtle and hard to understand. Now I want to go on to the intermediate ionization phase. So this is traced by carbon-4, and we're going to set the carbon-4 column density at 13.5, and again vary the density corresponding to these ionization parameters. The highest ionization parameter, lowest density that we have here, of 0.01 per cc, is giving rise to oxygen 6, so photoionized oxygen 6. We can actually go to a lower density yet and get a significant amount more of oxygen 6 in a photoionized phase at redshift 1. So that's an important point, and a difference with redshift 0 that we'll see later. The Lyman alpha profile does depend upon density in this case, because the more ionized we are, the less neutral hydrogen relative to total hydrogen that there is. And we see interesting differences, of course, in the shapes of these H1 profiles, depending upon the density. If we make a slightly broader C4 cloud, we see rounder and broader Lyman alpha clouds as well. And so I just wanted to show that because we're going to be superimposing these different phases in a little bit. Now we're going to look at a constant density and a changing metallicity. So the lower metallicity showing a lot of hydrogen Lyman alpha absorption. But you see how the shapes of these, even for the high metallicity case, the supersolar metallicity case, the shapes are different than they were for the narrower magnesium 2 low ionization phase. And so this rounded bit of the profile, we're going to see that that's necessary to explain certain observational data. The thicknesses of these structures can be significantly larger, particularly, of course, if we have a high ionization parameter, but they can also, for very high metallicity, be very small. And so there's a whole range of things out there producing potentially carbon-4 absorption as well in this intermediate ionization phase. So in this case, in some cases, for some densities, you can get low ionization and oxygen 6 absorption at redshift 1. These are often broader clouds, and that changes the way that they contribute to the Lyman series and Lyman alpha lines. The typical neutral column density for these are smaller than the low ionization phase, but their contribution to Lyman alpha can be very important, and even dominant due to their larger B parameter. And then the cloud thicknesses can cover a large range, but they're typically larger than low ionization phase clouds. Now I want to look briefly at oxygen 6, and this is going to be a collisionally ionized model where the oxygen 6 has a column density of 13.5, so relatively weak, and the temperature changing 5.3, 5.35, 5.5, and 5.7. We start to see the neon 8 just barely at 5.7, and we see carbon 4 at the lower temperature. So there can be carbon 4 from a collisionally ionized phase as well. These can be broader, and notice the hydrogen that there is a broad profile, and for certain lower temperatures, we see interesting wings here that are going to be important for explaining some observational profiles that it seems really cannot be explained in any other way. Here is the example of looking at the metallicity for a fixed temperature. And we see that the metallicity does not affect the ratios of the metal lines at all, as it shouldn't. And we see that the metallicity is a very important diagnostic of how strong, or I should say the other way around. The wings are going to be a very strong diagnostic of what the metallicity of such a collisionally ionized phase would be, relying on a temperature that can be determined by constraints from the metal lines. So the thoughts here, depending upon the temperature, these different species can arise from a collisionally ionized phase. The typical NH1 is really quite small, but it can be very broad. The density can't be measured, but it's likely to be small, and if so, they're kiloparsec scale most likely. And if we wanted to have pressure balance with this phase, this is the same thing that Todd said yesterday, it's easy to do. It's about 10 times higher temperature than lower intermediate ionization phases, and so the density would need to be about a factor of 10 lower. Let's put these phases together. Let's do a 3-cloud model where they're all 3 clouds centered at the same velocity. And so the low ionization phase, you see here in magnesium 2, the gold is the carbon 4 intermediate ionization phase, and then there is an oxygen 6 phase that we see in green. And we see how nicely these fit together to shape a Lyman alpha profile, which is shown in the dotted line here. So for the low ionization phase, the metallicity is very clearly going to be constrained by anything we see in Lyman beta and below, but even also by this little square region at the bottom of the Lyman alpha profile. One really does see this in observational data. The carbon 4 is going to be constrained by this region of the Lyman alpha profile. Right, so that's a little bit subtle, but also you need something to explain this. It doesn't do it for the bottom notch, but it will do it here. And certainly you can place a limit on it, because for any lower metallicity, it would exceed the observed profile substantially. The oxygen 6, when it exists, produces these wings, which also are sometimes observed, and so that can also be constrained, and the metallicity can be constrained. Okay. The sizes of these clouds, 4 parsecs, 160 parsecs, and then we're not sure about the O6 exactly without knowing the density. Okay, let's add in another cloud. This time it's another C4 cloud. We often see these that's offset by 15 kilometers per second. So these carbon-4 clouds are blending together and producing an asymmetric profile in the Lyman alpha. Again, something that we often see, as well as in these species. So the important point here is that we can constrain the metallicities for each of these by using little tricks in certain portions of the profiles, right? For the low ionization, it's the series lines. In this case, the square bottom isn't really doing it for us, but it certainly would for Lyman beta. In the case of the carbon-4 on the left, that one can be constrained by this left side of the Lyman alpha. The carbon-4 on the right is clearly constrained by this region on the right, and then the oxygen-6 by these wings. So it really is possible to separate these profiles into different phases, and several groups are working on this, on looking at variations of metallicity across a system. There was some pioneering work in 2019. Many people had done it more by hand for the last 2 decades, really, but now it's possible to do, a more rigorous Bayesian cloud-by-cloud modeling and infer metallicities and densities with error bars. Samir, my grad student, has one of these new methods, and his really relies on the shapes of the profiles, compares simulated profiles from cloudy to the data, and then optimizes what the parameters are in the different phases. And so here are some quick results from his paper, but I direct you to his 4-minute presentation on the YouTube channel, or his paper in Monthly Notices that's already available there, that you can see the variation in metallicity of different clouds across these 4 different absorbers, and how much more there is to see with metallicity compared to averages that can be determined just by a single column density. So the final point is, how do these structures evolve, and how do the absorption line profiles get affected by that? So a simple thought experiment here to do is, let's take the redshift 1 example that I gave, example 2, and let's fix the density to the same as in the redshift 1 case, the metallicity, the NH total, and the B turbulent for each of the components. So let's try to take a physical structure that existed at redshift 1, and let's plop that same structure down at redshift 0, where there's a different extragalactic background radiation. Really simple, nothing too terribly profound. Let's keep the collisionally ionized phase the same, though, having the same density and temperature, like as if galaxies were behaving the same way and the same processes were producing structures. But let's see what the absorption system would look like. So here was the case that I showed you a little bit ago at redshift 1. Notice the offset C4 cloud, the single component in magnesium 2, and the oxygen 6 with a little bit of a contribution from the C4 photoionized phase. Evolved to redshift 0, we're not seeing the same situation at all. We are seeing a situation where the magnesium 2 is stronger and would be detected in the offset C4 cloud. So if this cloud was alone, this C4 cloud, then this would be a magnesium 2 cloud at low redshift, but it would have a lower density than those. at higher redshift. So the whole population of low ionization absorbers at low redshift are on average lower density, especially the weak ones. Right? We see that the photoionized oxygen 6, which could have been considerably stronger if we had gone with a lower density, is absent at low redshift. And we see that at redshift 1, we could have a situation where we had more photoionized gas where that would completely dominate this collisional ionization. Okay.
Jane?
So, yeah.
I know you're just wrapping up now. I want to give people time for a little bit of a break. So I know this is your last slide. So immediately after this slide, people can join the breakout room and you can finish this discussion. And yeah, we'll start the other tutorial right at 9 a.m.
Okay, let me just finish up here. So what I wanted to say is that there can be hot gas in halos at low redshift. And why wouldn't there also be at higher redshift, that it might be hidden below a photoionized phase? And so because of this change, when we think of like halo covering factors for gas, we should think of gas of a certain density, not gas traced by a certain chemical species. So I'll just put up my closing thoughts, and people can take their break, if I'm allowed to share for just a tad longer.
Yes, you are. And actually, you're allowed to share this in your breakout room, which might be a good way to kind of transition to the discussion that follows this. Thank you so much for that masterclass in cloudy modeling. That's really great. As someone who's done it, but kind of in bulk, it's really interesting stuff.